Suppose that a car travels at 50 miles per hour for 2 hours. How far is the car traveled? Well, you probably know already the car must have traveled 100 miles. But let's look at this problem in a little more depth so that we can attach some mathematical meaning to it. Now we know that the car traveled at 50 miles per hour, so we know that its velocity was 50 miles per hour. We could write a velocity function that looks like this. V of x equals 50, where x represents the number of hours traveled. So no matter how many hours this car travels, the velocity is a constant of 50 miles per hour. If we graph the velocity function, we'd have something that looks like this, where the horizontal axis represents the time and the vertical axis represents the velocity. Now, where in this graph can we find what we know already? That if the car travels at 50 miles per hour for 2 hours, we know that it's traveled 100 miles. Well, let's think about this rectangle. We've got a rectangle that along the horizontal axis goes from 0 to 2 hours, and along the vertical axis it goes to 50 miles per hour. The 100 miles per hour that we know is the answer to this problem is coming from the area of the rectangle. 2 hours times 50 miles per hour is 100 miles. So what you can see from this is that the distance is the same as the area under the graph of the velocity function. Now we've actually seen velocity before. We looked at a problem like this, where we said if we know a function for distance, we can find a function for velocity by taking the derivative of the distance function. But in this case, we knew the velocity and we wanted to know the distance. So the distance function is the antiderivative of the velocity function. So now we know that distance can be found in two ways. We can either find the antiderivative of the velocity function to find a distance function, or we can find the area underneath a graphed velocity function. So let's see if we can use this idea of area to find a distance that an object has traveled. The velocity of a moving object is given by the function v of x equals 3x, where x is in hours and v is in miles per hour. Use geometry to find the distance the object has traveled during the first 3 hours, that is, when x is between 0 and 3. Now we know that if we graph this velocity function, we can use it to find the distance traveled. Since our velocity function is 3x, that means we're graphing a line that has a slope of 3 and a y-intercept of 0. If we want to know the distance the object has traveled during the first 3 hours, this is the part of the graph that we're looking to find the area of. It's this triangular region that goes from 0 to 3 on the x-axis. Now, since it's a triangle, we can use a formula for area of a triangle to find the area of this shaded region. The base of the triangle is 3 units long, or 3 hours long. The height of the triangle is a little trickier to find, but we do know that the point where this vertical line, where time is 3, intersects our velocity function, v of x equals 3x, has to happen where x is 3. So, to find that distance, we just substitute 3 in our velocity function, and we know that the height of the triangle is 9. So now to find the area of the triangle, we'll take 1/2 times the 3, which is the length of the base, times the 9, which is the height of the triangle, to get 13.5. So the distance that was traveled is 13.5 miles. What if we change one thing about this problem? In this case, we'll still have the same velocity function, but now we want to know the distance the object has traveled between the 3rd hour and the 5th hour. In other words, when x is between 3 and 5. We still have the same graph, but now we're looking for this area, the area that has x-coordinates between 3 and 5. Now that's a trapezoid, and we do have formulas for finding area of a trapezoid, which we certainly could use. We also could look at something like this. We know that this distance between 3 and 5 is 5 minus 3, or just 2 units. And we could split this area up into two regions that are a little easier to find areas of, into a rectangle and a triangle. The height of the rectangle is the same as v of 3. So the height of the rectangle is 9. And the height of the triangle is the difference between v of 5 and v of 3, which is just 6. So the area of the triangle is 1/2 times its base, which is 2, times its height, which is 6, and the area of the rectangle is 2 times 9, which is 18. So the total area is 24, which means the distance traveled is 24 miles. Now we've said that area under a graph can be expressed as an antiderivative. We looked at this problem where we were finding the distance traveled during the first 3 hours. In other words, when x was between 0 and 3 for our velocity function v of x equals 3x. Since that area can be expressed as an antiderivative, we also could use this notation to denote the area underneath this curve from 0 to 3. And for this particular graph, we've got an area under the curve between 3 and 5, so we could use this notation to show that the antiderivative is the same as the area. These two integrals are called definite integrals. The definite part of it means that we definitely know the x-coordinates between which we're finding the area. In the first case, the x-coordinates are between 0 and 3, and in the second case, the x-coordinates are between 3 and 5. In either case, the 3x is the equation of the line that's the upper bound for the shaded region. So what if we're given something in that notation? Use geometry to evaluate this definite integral. It's the integral from 0 to 4 of 2x dx. Well, all that means is that we have a line, y equals 2x, and we would like to find the area between that line and the x-axis, where all the x-coordinates of the points inside that area are between 0 and 4. Well, that's a triangle, so if we find the base and the height of the triangle, we can use our area formula for triangles. The height of the triangle is the same as the value of the function when x is 4. So the height is 2 times 4, which is 8. The base of the triangle runs from 0 to 4. So the base of the triangle has a width of 4, which means our area is 1/2 times 4 times 8, or 16 square units. So the value of the integral from 0 to 4 of 2x dx equals 16. Now if we have something like this, the integral from 1 to 5 of negative x squared plus 6x minus 5 dx, we're really asking the same thing. Find the area underneath this curve, between the curve and the x-axis, from 1 to 5, from x-coordinates of 1 to x-coordinates of 5. If we graph the function, we'll have this parabola. The problem is to find the area underneath the curve. We don't have a familiar shape. We don't have a triangle. We don't have a rectangle. We don't have a shape that fits an area formula that we're familiar with. So how do we approximate this as some area that we recognize? Well, we could say the parabola is 4 units wide, and maybe we try to make a rectangle that kind of sort of fits the parabola. So that rectangle's 4 units tall, so the area is about 16 square units, which is a little too big, isn't it? And it's a little too big because this rectangle doesn't quite approximate the area of the parabola. Maybe we'd want to try something a little bit different. And we're going to use something that are called Riemann sums. So a Riemann sum simply means that we're going to take this area and we're going to split it up into more rectangles that will approximate the area that we see underneath this parabola. So let's say we want 4 rectangles instead of the one big rectangle that we use to approximate the area. The width of each rectangle needs to be the same. So instead of going from 1 to 5, which has a width of 4, we'll split that into 4 equal pieces. So we want 4 rectangles that each have a width of 1. Now the issue then is, if each of these rectangles has a width of 1, what's the height of the rectangle going to be? So let's look at these rectangles one at a time. So let's take this first rectangle that has all the x-coordinates from 1 to 2 and make a decision about how we want to measure the height of the rectangle. Let's say what we decide is that we're going to look at the right endpoint on that interval from 1 to 2, and we're going to build a rectangle that's as high as the parabola at that right endpoint. So that's this rectangle. And we want to find the area of that rectangle. Well, we know that the height of the rectangle is f of 2. In other words, the height of the rectangle is the y-coordinate that goes along with the x-coordinate of 2 that we use to determine how high the rectangle should be. So this rectangle is 3 units tall. It's 1 unit wide, so the area of that rectangle is 1 times 3, or 3 square units. Now we'll move on to the second rectangle, which is the rectangle that goes from 2 to 3 on the x-axis. Remember, we said that we're going to use the right endpoint of that interval to decide how tall the rectangle is going to be. And in this case, the rectangle is going to be, well, let's see, how tall? The x-coordinate at that point where that vertical line meets the parabola is 3, so the y-coordinate that goes along with that is 4. So this rectangle is 4 units tall. It's still 1 unit wide, so its area is 1 times 4, which is 4. And we'll continue that all the way across. The next rectangle has x-coordinates that go from 3 to 4. We'll use its rightmost endpoint to determine its height. So the rightmost endpoint happened where x was 4 and f of 4 is 3. So the height of this rectangle is 3. Its width is still 1, so the area is 3. Now when we get down to the last one, this is a little strange looking. Here's our last rectangle. It has to have a width of 1. Its rightmost endpoint is at 5, but what's its height? Remember, we're going up from that rightmost endpoint to the parabola, and when we do that, we find that the height of that last rectangle is 0. So we really don't have a rectangle there. But we can still figure out its area, which is 1 times its height, which is 0, or 0. Now what we want is the total area. And the total area is the area of these 4 rectangles. Remember, there is a 4th rectangle that has a height of 0. The area of those 4 rectangles added together, which is 10. So what we've done is approximated the area under the curve by using these rectangles to make a guess about how much area is there. 10 isn't the exact area that's underneath the parabola, but it's probably pretty close because some of the rectangles are a little outside the parabola, and we're also missing some of the area that's inside the parabola. So between those two things together, we probably have something fairly close to the actual area underneath this parabola. Now we made a decision that we wanted to draw 4 rectangles to approximate the area, and that meant that the width of each rectangle was 1 unit. But then we made a decision about how we were going to measure the height of the rectangles, and our decision was that we were going to measure from right endpoints. If we had measured from left endpoints on each interval, this is what our rectangles would have looked like. And our area would have been a total of 10 square units. Once again, that would be an approximation of the area underneath the curve. If we use the midpoints of each of our intervals to determine the height of each rectangle, we'd have something that looked like this as our approximation. And the area of the 4 rectangles we would have from that would be just a little bit bigger, which would be 11 square units. So what we're going to find is that when we are approximating area under a curve using rectangles, we're going to have to make some decisions about what method we're going to use to approximate. Although no matter how we draw these rectangles, there's going to be some commonalities in how we approach the problem. The first thing we're going to have to figure out with any of these problems when we're approximating area with Riemann sums is we're going to have to find the width of the entire interval. In this case, the width was 4. We got that by taking 5 minus 1. We're also going to have to make a decision about how many rectangles we want to use to approximate the area. The more rectangles we use, the closer to the actual area we're going to get. But obviously, the more rectangles we use, the more computations we have to do too. We have to find the width of each of the rectangles, and the width of the rectangles we'll find by taking the width of the entire interval and dividing it by the number of rectangles. And then we're going to have to decide whether we want to use a left endpoint, a right endpoint, or a midpoint to determine the height of each of our rectangles. Now let's try that process on this problem. The Acme Widget Company knows that the marginal cost in dollars of producing X widgets is given by C prime of X equals negative 0.1 X squared plus 100X for X less than or equal to 500. Approximate the total cost of producing 500 widgets using 5 subintervals over the interval from 0 to 500 and the left endpoint of each subinterval. Now we could graph the function, but we really don't have to. We can figure out what the intervals are and what the rectangle's dimensions would be just by using the information that we've got. The width of the entire interval, which goes from 0 to 500, is 500 minus 0, or 500. We've been told that we want 5 subintervals, so we're finding the area of 5 rectangles. And the width of each rectangle is going to be 500, the entire width, divided by 5, the number of rectangles. So each rectangle will be 100 wide. Now here's where we might want to do a little bit of visualization without actually graphing. We know that our X values go from 0 to 500, and we're dividing that interval into 5 subintervals, which are each 100 wide. So we can think of intervals going from 0 to 100, 100 to 200, and so on, all the way up to 500. Now, since it's the left endpoint of the intervals that's determining the height of the rectangles, let's figure out what the left endpoint is for each interval. The first interval from 0 to 100 has a left endpoint of 0. The second interval from 100 to 200 has a left endpoint of 100. The next interval from 200 to 300 has a left endpoint of 200. The fourth interval has a left endpoint of 300. And the last interval from 400 to 500 has a left endpoint of 400. Now, let's expand that table so that we can put all the information that we'll need to find the area of all 5 rectangles. We already know the intervals. We know the left endpoint. We will determine the height of each rectangle from the left endpoint of that interval. We need to determine the width of each rectangle, and those two things together will tell us the area of the rectangle. So let's start with the first interval that has a left endpoint of 0. The height is the value of the function at that left endpoint, which is 0. So this is a rectangle that has no height. We saw that in the last problem, that it is possible that you have a rectangle with absolutely no height. So that's not really surprising. The second interval has a left endpoint at 100. So its height is c prime of 100, which is 9,000. The third interval has a left endpoint of 200. So its height is c prime of 200, which is 16,000. The fourth interval has a left endpoint of 300. So its height is c prime of 300, which is 21,000. And the last interval has a left endpoint of 400. So it has a height of c prime of 400, which is 24,000. Now all of the rectangles have the same width, which is 100. Remember, we got that by taking the width of the entire interval from 0 to 500 and dividing that by 5. And then the area of each rectangle is its width times its height. So the first rectangle's area is 100 times 0, which is 0. The second's area is 100 times 9,000, or 900,000. The third rectangle has an area of 100 times 16,000, or 1,600,000. The fourth has an area of 100 times 21,000. And the last one has an area of 100 times 24,000. So we've divided this area into 5 rectangles, and the total area will be the approximate total cost, which is approximately 7 million. Even without graphing, we can still find an approximation for the area